Heavenly Father, we thank you for this day. Again, Lord, we thank you for this time we have just to try to fill out some examples for this class and just look at the homework and so forth, Lord. And just help us to use this time wisely, Lord, for your glory. In your name I pray, Lord Jesus. Amen. I think it'd probably be helpful if I just did a couple of basic examples for you guys, just to, because I think that the video I had you guys watch, that has a nice kind of difficult example, right? And one kind of stupidly easy example. And maybe it'd be nice to have something in the middle, right? So, and but then we should probably have plenty of time for your homework questions. So here's the question. Well, first of all, some definitions. Probably should. So a definition, let's say S, a subset of Fn is linearly independent, right? If and only if what? For any, v1, v2, vk, taken from S, we find c1, v1 plus plus ck vk equals to 0 implies that c1 equal to c2 equal to equal to, well, let me just say c1 equal to 0 all the way on out to ck equal to 0. In other words, a subset of column vectors is linearly independent if and only if whenever you take a linear combination of them set equal to 0, it forces it to be the trivial combination, right? So computationally, right, you can check this, like calculationally, right? This is equivalent to the problem, I'm looking to solve v1, v2, vn times the vector c1, c2, ck equal to 0, implies, c, if I call this thing c, equal to 0, right? So that's a homogeneous linear system, right? So to check linear independence of a set of vectors, we just have to show that the homogeneous solution to that system of equations has only the 0 solution. That gives us linear independence of the vectors. That was one definition we looked at. In fact, that's the second definition I looked at in the video, right? The first definition I looked at was what? What'd I say? The span of a set, right, would be what? This would be the set of all finite linear combinations taken from S. So in particular, this would be, something like C1, V1 plus plus CK, VK, such that V1, V2, VK are in S. Oh, there's something I've forgotten to say here. In fact, for both of these, I really should say, I'm sorry, kind of an important aspect of this. So I really should put it right here. C1, C2, CK, and where? Right, in the field. Sometimes I forget, because the field's kind of just always there, But it is true. If we worked over different fields, we get different spans. Sorry about that. So again, the basic idea here is that, this set S we're using to generate this space, right? And to say if S was also linearly independent, that means in some sense that that generating set is kind of as small as it can be. We'll make that precise with the theory as we go on in here. But let's just look at two examples. So example 1. let's look at S equal to, let's say, 1, 1, 2, 3, and then 0, 1, 1, 7. Let's see here then. 2, 1, 3, minus 1. And then 2, 2, 4, 6. All right. You know, is this set linearly independent or is it linearly dependent? If it is linearly dependent, exhibit linear dependencies, if you will, which are found here. Okay? So what do? We look at the, first of all, let me give these things some names because that'll help our discussion. So may I suggest V1, V2, V3, V4, right? All right, so we're going to look at the matrix of S. So this is notation, guys. If I have a set, it's a finite set of column vectors. If I do this, if I put like brackets around the set, what that means for me, it's just the corresponding matrix made by gluing together the vectors in that order. So I guess I'm also assuming that that the set has some ordering on it, which you guys don't usually. I don't usually have linear algebra students go, "Hey, we never said these were ordered sets, so this is ambiguous." Like you could put V2 or V1 first, which one, you know, how do you? It's well, just if I write this, I'm assuming that it's ordered, obviously. Otherwise, it would be ambiguous. But anyway, so that matrix is a 4 by 4, right? We got 1, 1, 2, 3, 0, 1, 1, 7, 2, 1, 3, minus 1, 2, 2, 4, 6, right? Do you guys know how to do row reduction? You see more examples of this? I'm sensing no. So let me show you. I'll do some row reductions for a different problem later. How about that, okay? We'll actually calculate the inverse by row reduction explicitly. Let me save my energy for that. Let's just do this with the website. I mean, of course, you could use MATLAB or Mathematica, whatever floats your boat. Hey, come on. Wake up. Come on. This is the website I've mentioned to you guys before, I think. How many rows are we looking at? 4 and, oh, why don't I have to, I mean, the augmented coefficient matrix of this would be what? Why did I have an N here? You guys should stop me. It's supposed to be K, obviously. You know, the last one is 0, right? So this is one of those homogeneous systems. We don't even really need to tack on the last column because we know under row operations it's just going to stay 0. So as long as you remember the interpretation, we can get away with using the truncated augmented coefficient matrix, and in particular just the coefficient matrix. So it's a 4 by 4. And what do we got here? Fortunately, I don't have eyes in the back of my head. Can you read to me?
Going across 1, 0, 2, 2, 1, 1, 1, 2, 2, 1, 3, 4, 3, 7.
Oops, sorry. 7.
-1 and 6.
All right. So prediction. When we do this row reduction, what's going to happen is we're going to have 2 non-zero rows. All right. The fourth column is going to end up being, going to end up being 2, 0, 0, 0. This column, after the row reduction, is going to end up being 2, minus 1, 0, 0. Now, what do you know? So, just a second here. Let me, we still have these fascinating things on the wall called light switches in this room. This building is like time traveling, you know. As you go to the lower floors, you get, you know, you get to live in a time where you are more free to control your environment. So you go up, it gets smarter, and you lose control, you know. Like your ability to turn off and on the lights in a room becomes a whim of the IT department here. Here they still trusted us with light switches, which is really kind of nice. But as you can see, check that out. What do you know? It's what I just said, right? The fourth column is 2, 0, 0, 0. The third column is 2, minus 1, 0, 0. How on earth did I know that was going to happen? So we do row reductions, right? And so this symbol right here, if I just write that, this means row equivalent, and I just don't feel like telling you the details. So you can also try using that, and depending on the instructions of the problems, it may or may not hurt you. I mean, if I say, show me the Gaussian elimination step by step, explicitly indicating which row operations are used, and then you use this symbol and tell me the answer, then I'm probably going to take all your points away. Let's see here. Yeah, 2, 2, 0. I mean, I'll give you something. At least you could copy your neighbor's answer, right? But, no, sorry, we can do that. We don't do that. Don't do that. Okay, so yeah, that's after. Apparently, I shouldn't have been too afraid of this. How many row operations did it take? 1, 2, 3, 4, 5. Not too bad, right? 5 row operations. This would actually be a somewhat decent test question, a reasonable test question. This row reduction, not the most pleasant for me to grade. I usually find a 3-row operation matrix is plenty enough to show me whether or not you guys know what you're doing. Usually enough, I can tell. But anyway, so there it is. So is this a linearly independent set then? Is S a linearly independent set? What does that matrix say about the system of equations, you know, taking linear combination and setting it equal to 0? What's it say about that? Let me be more explicit. What does it say about the system of equations C1v1 plus C2v2 plus C3v3 plus C4v4 equal to 0? What can you tell me about that system of equations? Does it have only the 0 solution? What is this matrix? I mean, this is just the shorthand for this, right? Here's the full augmented coefficient matrix for that system, right? And this tells me that, in fact, I can choose C1 equal to what? Minus 2C3, minus 2C4, and C2 equal to what? C3, right? And this is for what? Any C3 and C4 in the field we're working over, which is, you know, you can make it the reals, or I mean, I guess I didn't say, but I mean, there's surely some trick problem where I could give you a set of vectors that would be, you know, linearly independent over a field of order 17, but they would be linearly dependent over a field of order 3 or something silly like that. I mean, there's probably problems like that, but I'm not thinking about that. When I write something down, I don't tell you which field. I'll admit, I'm usually just thinking reals. It's my default, okay? If you're ever in doubt about that, just ask me. So again, is this a linearly independent set? No, certainly not. I mean, you can put C2, C3, and C4, whatever you want, non-zero, and we have solutions. What are the linear dependencies we see here? So I presented the column correspondence property. Did you guys understand what I said there, what it meant? Probably not. So if we look at this, any linear dependence seen in the columns of the reduced row echelon form of the matrix, they're also present in the original matrix. In fact, the column correspondence property, the CCP, or linear correspondence, what's it say? It says any linear dependence of columns found in A is also found in a row equivalent B. In other words, if you do row operations to a matrix, it preserves whatever kind of linear dependence is present between the columns of the matrix. That's most interesting when we apply this principle to the reduced row echelon form, because if you look at the reduced row echelon form, it is utterly easy to see linear dependence in the reduced row echelon form. Like, what are the linear dependents here? I mean, I think I labeled them R1. I mean, I need to come up with some, I'm going to use R1, R2, R3, R4 just to give it a name. So can you tell me how R1, R2, and R3, R4 related here? Like, what's R3 equal to? Yeah, 2R1, right? You say minus R2. Yep, very good. And R4? 2R1, right? Now, that statement, again, about the reduced row echelon form of the matrix, but the linear correspondence tells me that those same patterns are evident in the original matrix. That's the column correspondence property. That's the linear correspondence. And over here, they're not as obvious, right? We can also say that V3 is 2 times V1 minus V2. And you see that's a non-trivial observation, right? If you take 2 times V1, what do you get? You get 2, 2, 4, 6. 2, 2, 4, 6 minus 0, 1, 1, 7 gives us 2, 1, 3, minus 1. I personally happen to know this because that's how I made up the third column in this example. But and then I made up the fourth column by just multiplying the first one by 2. That's why I was so sure that the reduced echelon form was going to have the form it does, because I understand the column correspondence property and the rights and privileges that I'm entitled thereunto. Let's see here, so 2 times V1. So yeah, that's the column correspondence property, most nicely seen in comparing A versus reduced row echelon form of A, linear dependence of non-pivots on pivots columns can always be seen. That's essentially by the definition of pivot columns, right? Think about pivot columns. They have the leading ones. Non-pivots either are 0 or they're built from non-zero things that were in the same place that the pivots were, which means you can always build every non-pivot from a linear combination of pivots. It's kind of like saying everything under, everything under a set of stairs falls in the shadow of a step. kind of an inescapable statement, this one. Any questions? Yeah.
So if it's linearly dependent, then you'll end up with rows of zeros at the bottom? Or is there a term you wouldn't?
You could have rows of zeros at the bottom and still have linearly independent.
But if it's linearly dependent, there will have to be a row on the bottom.
No. Not true. Would you like me to show you? Okay. Let's see here. For the, well, I'll start with yours. What did you said? If linearly dependent must be. Well, you said the other way around. You said if there's a row of zeros. If row of zeros at base, right, of reduction of reduced matrix, that implies not linearly independent, right? That was you're trying to game my system and avoid the logic, just come up with some sort of greedy algorithm to not think through my definition, right? I get it. I get it. Listen, like, you know, we state definitions because of their logical minimality. Like, you really need to use the definition. Don't try to come up with some sort of overarching calculational way to do it. It's not going to go well for you because there's so many stupid cases. Like, so what I'm trying to say about, maybe something like this. 1, 2, 3, 4, 5. 0, 1, 0, 0, 1. And 1, 0, 0, 0, 0. All right, this set. I won't actually do it, but if you calculate the reduced echelon form of T, what you will get is this. Two rows of zeros at the bottom, but that is linearly independent. So saying there's rows of zeros at the bottom implies linear dependence won't work for us, right?
So if you have one of the C's that you're solving for as a parameter, then it's linearly dependent?
That is true. If there is a C which appears as a parameter, it's linearly dependent. That's fair, because that is equivalent to saying that 0 is not the only solution, right? Is there another way you could say it? Well, let's go back to his. What was yours?
If it's linearly independent, then there will be a row of what? Oh, linearly dependent. Yes.
Oh, I guess my example works for yours too, huh? Oh, no, well, not exactly. I mean, this is kind of against yours, but not, I think you're actually after something else. So for you, let's look at the set T2 equal to, say, 1, 3, 2, 6, 0, 1, like that. So here's a subset of I mean, I can view it as a subset of R2, let's say, just to be specific. And if you do the row reduction on this, right, I can tell you by the column correspondence property that this will have reduced row echelon form. 1, 0, 2, 0, 0, 1. This is certainly a linearly dependent set, and yet it has no row of zeros on the bottom. Right. So we can't tell anything directly from seeing a row of zeros on the bottom. It's not about a row of zeros or lack thereof or presence thereof. What is it? What it's about? What's the real issue? I mean, what she said is right. I mean, if there's a parameter in the solution set, it's linearly dependent. Can we say that in terms of columns? What is it? How do you detect there being a parameter in the solution set in terms of columns? What's that mean? Let me circle the offending columns. This one. There was no offense here. This was linearly independent. Over here, this column and this column, the trouble. In terms of failing to have a zero, just a zero solution, right? Pivot. Sorry. It's okay. You were thinking. It's okay. Thinking is allowed. That's good. But yeah, I was just saying these two columns are offensive in terms of their just being a zero solution because these are non-pivot columns. So the thing that you could say overarchingly is if when you do take your matrix corresponding to the set of vectors, you do the row reduction, if the resulting matrix has non-pivot columns, even one of them, it's linearly dependent. If it only has pivot columns, it's linearly independent. That's what we should say. It's not about like row of zeros at the bottom or something like that. Does that make sense? These are good questions. I wish students would ask questions like these more before I ask questions on the test about it. It's good. What could we say for my example one? Anything interesting? I think we could say this. For example, V3 is an element of the span, right, of V1 and V2. We could say that. Yeah? Is V4 in the span of V1 and V2? Yes, also. And why is V4? I mean, let me write the evidence for these claims. It's simply this. V3 is 2V1 minus V2. That's a linear combination of V1 and V2. V4 is 2 times V1. That means it's a linear combination of V1 and V2. By the way, these do not have to be complicated ideas. They're actually very simple once you like totally grasp the idea. You'll find it's actually not that hard. Yeah.
So when you're setting it equal to 0 for the augmented coefficient matrix, like when you put the row of zeros in,
Column zeros, but yeah.
Because you're essentially checking the definition to see if it's true?
Right. Precisely. This is the calculation which checks on the implication in the definition. So, I mean, the sort of, if you will, I guess we don't say this here, but primordial definition. No, we can't say that. The basic definition, the initial definition that we gave, just in terms of, well, it should be linear dependent. Set's linearly dependent if you can write one vector as like a linear combination of the others in the set, right? Well, to check that for a given set, you'd have to check each vector one at a time to see, is it a linear combination of everything else in the set, right? And then you have to go to the next vector and check, is it a linear combination of everything else in the set? And the next vector, is that a linear? I mean, that would be awful to actually computationally do that, right? So it's quite wonderful that we have this theorem that linear independence is equivalent to saying, well, if you have any linear combination, C1 through, C1 V1 plus C da 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 CK VK equal to 0, that implies all the coefficients have to be 0. That's equivalent to saying any vector can be written as a linear combination of the others because it's just so much logically easier calculationally to deal with, as I call it in the video, King's definition. Yeah. Also, for what it's worth, if you work on linear algebra over things more general than fields, you'll find out that this actually has to become the definition of linear dependence because like it doesn't work. The other definition I stated actually doesn't work if you go beyond fields. I found that out the hard way last year. But anyway, yep.
Over here where you wrote V3 is an element of span set V1, V2, why is it just of V1, V2? Why'd you pick those two out of all the V's?
Oh, because V1 and V2 in this case are the pivot columns of the S matrix. Because I already wrote down these linear dependences from the column correspondence down there, right? So I knew, I already had in hand that I can build V3 as a linear combination of V1 and V2, and V4 as a multiple of V1. Remember that the span, that's just notation for the set of all possible linear combinations of the things going into the span.
So you only build linear combinations off of pivot columns?
You can build linear combinations off whatever you want. I mean, you don't have to have a minimal set. I mean, you know, we could take a plane. The plane could have the vector, 1, 1, 1. You could have the vector, 2, 0, 0. We could look at the span of those, all linear combinations of those. Those would fill out a plane, right? If you want, I can stop my angle bracketing. Sorry, it's my calculus 3. It gets me thinking about angle brackets. But anyway, if you take and add these, what happens if you add those together? What's the sum of these two vectors? It's, 3, 1, 1. Right? So, in fact, this would be equal to the span of 1, 1, 1, 2, 0, 0, comma, 3, 1, 1. I mean, adjoining this vector 3, 1, 1 doesn't add anything new. In fact, that's already present. This is a this set right here, linearly dependent. This set right here is linearly independent. By the way, something I have not, I don't think, mentioned in class yet, but I will try to emphasize Friday most likely, because it shouldn't just be you guys who hear it. Linear independence for a set of two vectors is especially easy. How can you tell whether or not two vectors are linearly independent or dependent? Hey, let's work it out from the definition. Well, from the King definition, right? If you have C1v1 plus C2v2 equal to 0, implies that C1, C2. I mean, that would be linear independence, right? So what if one of them is non-zero? You can either do, V1 equals to minus C2 over C1 V2, or you could do what? V2 equals to minus C1 over C2 V1, right? And if you think about this harder, and I'll try to work through it carefully Friday, or maybe I won't. In a nutshell, to check for linear dependence of two vectors, you just need to see is one a scalar multiple of the other. So I don't need to do a calculation to check for linear dependence in two vectors. I can just look at it and know. See, I look at these. Is 1, 1, 1 a scalar multiple of 2, 0, 0? No, I mean, if I multiply this by 2, I get 2, 2, 2. The 2's match up, but the 2, 2 and the 0, 0 don't match up, right? It's not a scalar multiple. So, anyway. So we have this result, VW linearly linearly dependent if and only if V is equal to K times W for some K in the field. Yeah.
When you say V3 is in the span of V1, V2,
Yeah.
you could add V4 to that and it wouldn't change anything, right? Like it would just be 0 in that case.
What do you mean? Add V4 to what?
This set that you're taking the span of.
I could put a V4 here.
Yeah, that wouldn't change V3 being an
Oh,
unknown, right?
that is true. In fact, this set would be equal to the span of V1, V2, V4. Yeah. Because V4 is already in there.
But that new span is not linearly, but that set is not linearly.
That is true. The set V1, V2, V4 would not be linearly independent.
Spans of unequal sets can be.
Oh, yes. Yes. In fact, finding a generating set which is linearly independent is a special thing. There are two different concepts at play here. The one is linear independence. The other is spanning. These are not the same thing. They both go together to give us something called a basis, as we'll learn soon enough. We'll soon learn that if we have a linearly independent spanning set for a set, it's what's called a basis. That's why I've used the term standard basis for E1 through En, because it serves that role. We could prove that E1 through, do you want to prove that? Let's prove. Here. I don't know, I'm not sure this one's almost too simple to be helpful. I'll try it though. E1, E2, En, a subset of Fn is linearly independent. So check this out. Proof. It's really stupid. So C1E1 plus C2E2 plus plus CNEN equal to 0, right? Suppose this. Thus what? What is that actually? If we write it in the comma ... notation, what is it? I give you guys control. Do you want me to calculate the jth component of this, or do you want me to just write it out in the comma ... notation? What's your preference? Index or list? List. All right. So this is C1, C2, ... Cn, right? And what's this? This is 0, 0, right? So by the construction of the Cartesian product, right, by our assumption of how we look at tuples, two tuples are equal if and only if what? They have to match component by component. What does component by component matching give us here? Yeah, C1 equal to 0, C2 equal to 0, Cn equal to 0. Therefore, E1, E2, En is linearly independent. This is that problem you have in the homework. Maybe it needs an induction. I don't know. I can't remember. Went towards the end of your homework, maybe. Oh, I'm sorry. I'm in mission 3. Ignore me. Yeah. I'm thinking mission 3. It's like way into next week of your existence. So, you want to do any time traveling? All right, let me shut up. Do you guys have questions about homework? I hope does that help? I don't know. Listen, this column correspondence property is if you don't understand it already, you need to meditate on it and come to an understanding of it and ownership of it. It is lifeblood for certain problems. There are problems that if you tried to do them with equations and basic definitions, yes, you could do them, but they would take you a half hour. With the column correspondence property, they're a minute or two. Part of the reason I did badly, personally, in graduate linear algebra when I took it as an undergraduate, is because I took undergraduate linear algebra over the summer with a very good professor, but from a very bad book. This very bad book did not have the concept of the column correspondence property or the linear correspondence. I won't name the book, but I'm pretty sure the lack of this concept in my book was damaging to me. And we only realized, I mean, like, my brother and I only really realized it years later. It finally kind of dawned on us, oh, that's why everything was so hard. If we'd just known this, everything just junk. But anyway, I don't think it gets emphasized enough in certain discussions, which is why you see a slight overemphasis of it in my course. So. I guess the thing with the column correspondence properties, it's not about solving a particular linear application. It's not about fitting a curve to data or solving a system of equations arising from an electrical circuit or whatever else, which the modern course in linear algebra has become obsessed over problems at the cost of the theory, unfortunately, all too often. So. Okay, so guys, you want me to ask me about something before I rant on here? He's going to stop me. Mission 2, right?
On problem 28, it says find out Li set in R4. How / is that different from solving in like C4?
Well, we wouldn't talk about Z4 because Z is not a field.
Oh.
But it wouldn't be particularly different from, say, Q4, or I guess for that you could do Z5 for. I mean, any field where you have 1, 2, 3, 4. But anyway, that's. I mean, I just made it R4 to make it specific there. So to work problem 28, pretty much all you need to do is put those 4 vectors into a matrix and do the row reduction. You know, if we just have pivot columns, it's linearly independent. If we don't, it's linearly dependent, right? And you should not just, I mean, so here's the trap. You guys will, some of you will just write down the row reduction and put a yes or no. Like, that's not going to work. You need to, like, write the row reduction, explain what it means. You know, this is a 300 level proof-based class, math class. So you have to do calculation with explanation, right? So, just a warning. Other questions?
Problem 22.
Uh-huh.
This problem then says find the solutions after 3 cases.
Ah, yes.
It doesn't say what cases.
Yes, part of the problem is to find those 3 cases. So there you have x plus ky equal to 2, kx plus 4y equals to 1. And so I think what I found is, I mean, you could do row reduction on it if you wanted. You could, you know, do multiplication by the inverse matrix, the 2 by 2, so you've got a formula for it. If you try multiplication by the inverse matrix, you'll notice that the denominator for the formula will not make sense for certain values of k, right? In fact, there are 2 values of k that it won't make sense for. And you can look at the equations for those 2 values separately, and you may or may not find solutions. I mean, the solution set can be the empty set. That's one possibility. I really can't say much more without solving it. Yeah. But the 3 cases involve different values for k. I mean, I'll tell you this. It's like k is equal to 1 value, k is equal to another value, and then the third case is all other possible values for k. Does that make sense? Yeah. Uh-huh.
we found two different cases that were the same case. Do we have to put those both, like, say, you said there are two cases, there are two values of k.
Oh, you mean the solution set's the same for two different cases? I guess you're
Like,
grouping two of the
you said-
cases.
You said there were two values for
Well,
which k is
I'm looking at the three cases as the three different, values for k. Maybe you're just
Okay,
you're thinking of the different cases as being the solution set.
okay.
I mean, maybe I should just not give hints. I don't know.
Okay, no, I think that's it.
Yeah. I am now remembering the other thing I need to do for you guys, which you will ask me about soon. So let me see if I can do this one. I think this will answer the questions you're about to ask, if I had to guess. So suppose we look at 1, 3, 2, 6, right? Row reduce this thing. So here's A. So row 2 minus 3 times row 1, 1, 2, 0, 0. Oh. Well, that was rather uneventful. So look, there's the reduced row echelon form of A. So check this out. So we have E of row 2 minus 3 times row 1 is equal to what? This is equal to, what's the elementary matrix which does that? Uh-huh. And so 1, 0 minus 3, 1 times A is equal to, the reduced row echelon form of A. So, I mean, that's a very stupid case of a couple of your problems. Is A invertible? I mean, the point is, you can always write a product of elementary matrices times A giving us the reduced row echelon form. This is true whether or not A is invertible. Now your row of 0 comments is welcome, because we're talking about a square matrix. If there's a row of zeros in the reduced row echelon form, it's not invertible. And danger of answering student questions is they can be taken out of context, and there's a context in which everything is true and false in here for a given statement. But so is A invertible? Well, this is not equal to I, right? So therefore, A inverse does not exist. A separate example, if I had A equal to 1, 2, 2, 1, well, row reduce this thing. Row 2 minus 2 times row 1. Minus 3, is it? And then I'll rescale row 2. And then I'll take away 3 of row 2 from row 1. Or rather 2. Aha. So the reduced row echelon form of A is the identity matrix, which goes to show you that, what's that tell me, among other things? Yeah, A inverse exists. And more than that, that means that we can write, let's see here, what's this one? Row 2 minus 2 times row 1 is 1, 0, minus 2, 1. That one is 0, 1, 0, 0, minus 1/3. Notice that I'm writing them this way. That last one was row 1, 1 minus 2, 0, 1. So these matrices, right, my E1, my E2, my E3, and my typical numbering, although I'm not universally addicted to that numbering Don't read too much into the numbering. Think through the numbering in a given problem. That times A is equal to the identity matrix, yeah? So what's, you can write the inverse matrix as a product of elementary matrices immediately, right? So among other things, this tells me that A inverse is, E3 times E2 times E1, where they're given as I just wrote them here. Yeah?
I could just be missing this. Should E3 be 1, 0, negative 1, 2? Since you did row 2 minus 2, row 1.
Where, what, which one?
E3 you have as 1, negative 2, 0, 1. But you did row 2 minus 2, row 1. Or did you just go back?
No, they go, this is E1.
That's E1.
This is E2. This is E3. You got to be careful about that. The one that multiplies on the left first gets listed last as we read left to right. It's kind of like function composition. It'll catch you off guard if you don't think through it. Now, there's A inverse written as a product of elementary matrices. Can we write A as a product of elementary matrices? Yes, we can, right? A is A inverse inverse, by the way, which is E3, E2, E1 inverse, which by sock, shoes is E1 inverse, E2 inverse, E3 inverse. Did I have enough socks on? I don't remember, but it would just be socks. Anyway, it's that. And of course, those, to be explicit, I mean, here it is explicitly. E1 inverse is what? It's 1, 0, 2, 1. E2 inverse is 1, 0, 0, minus 3. E3 inverse is 1, 2, 0, 1. There you go. Multiply those three matrices out. Those are elementary matrices. Their product gives you A. I hope this, if you had any lingering doubts about, I had like 3 problems about these, right? So one of them I don't give you any room for. I just say find it as a product of elementary matrices, right? I'm kind of telling you it's invertible there. The next problem I sow some seed of doubt, if it's possible, right? When would it not be possible to write A as a product of elementary matrices? If its reduced rational form is not the identity, we cannot write it as a product of elementary matrices because it's not invertible. But we can still find elementary matrices such that those matrices times A gives us the row reduced. I mean, that's always there. And as I will prove to you guys next class, that is ultimately the motivating, that really is the calculational bedrock that gives us this column correspondence property. I'll derive the column correspondence property from this elementary matrix thing again. It's actually not that hard. Oh, I said I'd do a calculation of an inverse for you guys, right? Would that be helpful, or do you pass that? How big do you want? Oh, wait a minute. 3 by 3, 2 by 2, what kind of size are we looking at here? 3 by 3, all right, making me work for it. All right, so let's suppose we want to find the inverse of 1, 0, 6, 7, 8, 10, 0, 1, 1. If I'm very unlucky, this won't have an inverse, all right? But that's the thing, is we can go into the inverse finding algorithm, and part of this algorithm is, if it's possible to find the inverse, it finds it. If it's not possible, it gives us a proof that it doesn't exist. So here's the thing we do. We put this matrix, 1, 0, 6, 7, 8, 10, 0, 1, 1. My examples never seem to have negatives in them in class, isn't there? It's weird, huh? But I don't know, it's just me. I try to keep it positive. see here. So you take the matrix you're given and you concatenate it with the identity matrix, all right? And then the thing is, if you do row reductions, right, this is going to be equivalent to the reduced row echelon form of A, right, with stuff. And I explained in the video that the star, the Pac-Man, the ghost, those are solutions respectively to AE1, well, rather, it's like, well, anyway, I explained the theory in the last thing, right? So let me get back to work here. So we had to do some row reductions. We got row 2 minus 7 times row 1, which is what? 1, 0, 6, 1, 0, 0, 0, still 8. Oh, 40, bless you, minus 32, minus 7, 1, 0, yeah, 0, 1, 1, 0, 0, 1. Oh, I feel strongly about a row 3, row 2 swap. Yeah? I like row 3 for row 2. Do you? It's like, you know, row 2's been making all kinds of noise at night, and I heard row 3 doesn't stomp around at night, and I just want it for my upstairs neighbors, so have them swap apartments or whatever, 0, 0. My friend Somber Paul, I don't talk about as much as the Crazy Paul, but on occasion I'll talk about Somber Paul. We used to always have our study group go meet in his apartment. Study group consisted of me, Somber Paul, Crazy Paul, Jeff, mostly just us. But Somber Paul's theory was that his upstairs neighbors, for some reason, had toilets. Not installed, but they just like to take the toilets and just pick them up and just drop them on the floor, just chunk like that. For some reason, like at 2 in the morning, that was what they did. They just moved toilets around upstairs. That was the only way he could explain the noise. So it's like it's a random story from my undergraduate days. I don't know if you've ever experienced living in apartments. Yeah, I guess some of you are probably experiencing that right now. Row 3 minus 8 times row 2. Yeah. I guess dorm life is its own set of adventures. Let's see here. 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. So we got rid of the 8. And if we subtracted, that makes a minus 40, right? And, oh, yowzers. Oh, well, that still stays minus 7. I'm not looking forward to the step after this. 1, 0. Right? Now we got to clear out above the 40. Let's see here.
Should that be minus 8 in the bottom right row, since you did 8 minus row 2? You did 0. Very bottom right of the former identity matrix. Row 3 minus 8 row 2, there's a 1. There's a 1 in row 2 over on the far right.
Far right column. Yeah.
Oh, so that's supposed to be a... Oh, that just makes it worse. But thanks. It's even more. All right, fine. So, tell you what, I'll rescale this thing. Row 3 divided by... You know what, I won't. Let me just do things different for a change. So we could take row 1 plus, let's see here, 6 over 40